Let's continue with tracking the size of allocated regions. Let me just minimize it a bit. So you might have noticed the interface to free void PTR does not take a size parameter. Thus, it is assumed that given a pointer, the malloc library can quickly determine the size of the region of memory being freed and thus incorporate the space back into the free list. So the malloc library, given that it does not provide, it was not provided a size by the program, such as this free void PTR, it doesn't have the parameter. Therefore, the malloc library should be able to determine the region of memory being freed and thus incorporate or delete that and then make that space available for another process. To accomplish this, uh, task, most allocators stores a little bit of extra information, a header block, which kept in memory. So to accomplish that without having to input the size, to automate that, this is where the size that we talked in the previous video comes in, usually just before the handed out chunk of memory. Let's look at example figure 17.1. In this example, we are examining allocated block of size 20 bytes pointed to by PTR. So it's a size 20 bytes pointed by PTR. Imagine the user called malloc and stored the result in PTR. So if the program called malloc and then store this result in PTR, like PTR equals to malloc 20. So let's say the program called that. This is what it looks like. So an allocated region plus header. So when the program calls this PTR equals to malloc 20, it doesn't just allocate this 20 bytes. It also allocate a header, but it is hidden by malloc library. The header minimally contains the size of the allocated region, in this case 20. So the header contains that size, which is equals to 20, like this. It may also contain additional pointers to speed up the allocation. So there's also another pointer like magic, a magic number to provide additional integrity checking and other information. Let's assume a simple header which contains the size of the region and magic number, like this. So again, the header minimally contains the size of the allocated region, in this case 20. It may also contain additional pointers to speed up the allocation. So these additional pointers, aside from the header, is the magic number. So it provides additional integrity checking and other information. So let's assume a simple header which contains, so again we will start with a simple and then relax it as we go. So let's assume a simple header which contains the size of the region and a magic number. So here a size, int size, so type def struct int size and int magic, and then header t. So we define it like this so that we can use this header t method to our data structure for other code. So here an example above would look like what you see in figure 17.2, which is this. When the user calls free PTR, the library then uses simple pointer arithmetic to figure out where the header begins. So instead of remembering the size, this malloc library use this simple pointer arithmetic to figure out where the header begins. So this look like this, size and magic. But then if we use free PTR in our program, and then the malloc library will automatically uh, convert that into this. It uses simple pointer, so it uses pointer arithmetic to convert it and then trap into the kernel to actually manipulate the space, the physical heap space. So here, simple pointer arithmetic to figure out where the header begins. So void free void PTR. So since this is where what's the application inputted, and then it used the header underscore t asterisk hptr equals to header underscore t asterisk ptr minus 1. After obtaining such a pointer to the header, so after obtaining that pointer, after the malloc library convert that using pointing arithmetic, the library can easily determine whether the magic number matches the expected value as a sanity check. So assert hptr magic equal 1 2 3 4 5 6 7. So it uses like an equal operator in its other code, since it's a library, to check if it's does match the magic number as well as the header, and calculate the total size of the newly freed region via simple math. So after it equates that, it just use a simple math operator in the back end to be able to determine the size. So adding the size of the header to the size of its region. For example, it started with the 16 kilobyte address, and then it allocated for with a header, for example 20. Since it's 20 bytes, you just need to add 20 bytes to that 16 kilobytes starting virtual address, and then the compiler will then tap onto this physical heap space. Note the small but critical detail in the last sentence. The size of the free region is the size of the header plus the size of the space allocated to the user. So again, it's size of the header plus the size of the space allocated to the user. So again, because you have this header as well as this bytes, and this size or header size is hidden to the user, that header size is actually included in this overall allocated space. Thus, when a user requests n bytes of memory, the library does not search for a free chunk of size n. Again, thus, when a user requests n bytes of memory, the library does not search for a free chunk of size n. So thus, when a user requests n bytes of memory, the library does not search for a free chunk of size n. Again, thus, when a user requests n bytes of memory, the library does not search for a free chunk of size n. Rather, it searches for a free chunk of size n plus size of the header. Embedding a free list. Thus far, we have treated our simple free list as a conceptual entity. It's just a list of describing the free chunks of memory in the heap. But how do we build such a list inside the free space itself? In a more typical list, when allocating a new node, you would just call malloc when you need space for node. So a typical list in C, you just need to call malloc when allocating a new node. So how do we build such list inside the free space itself to be able to create this free list? Unfortunately, within the memory allocation library, you can't do this. Instead, you need to build the list inside the free space itself. So you cannot just call malloc and then create itself. You need to create it inside the space, available space itself. So we will gonna provide that example. Assume we have 4096 byte chunk of memory to manage, like the heap is 4 kilobyte out of, for example, 16 kilobyte physical memory. To manage this as a free list, we first have to initialize said list. The list should have one entry of size 4096 minus the header size. So here's the description of a node of the list. So type def struct underscore node underscore t in size struct underscore node underscore t asterisk next colon node t, then head. So now let's look at some code that initialize the heap and puts the first element of the free list inside that space. We are assuming that the heap is built with some free space acquired via a call to the system call, like mmap, like this call. This is not the only way to build such a heap, but serve as well in this example. So here is the code. Node underscore t head map null 4096 prot read prot write map 10, etc. We heap size equal 496 heap next equals to null. So remember, this heap are the first allocated space after the operating system. After running this code, the status of the list is that it has a single entry of size 4088. So once we run this code, it starts with 4006. Notice how it uses the header here with node underscore t in size structure node underscore t. While here, this node t actually uses our previous header t underscore t. Yes, this is a tiny heap, but it serves as a fine example for us. Here, the pointer contains the beginning address of this range. Let's assume it is 16 kilobytes, though any virtual address would be fine. So this is the head pointer. It starts with virtual address 16 kilobytes. So let's say from like available 64 kilobytes in our physical memory, we started from 16 kilobytes where the heap are allocated. Though any virtual address would be fine. Visually, the heap thus looks like what you get in 17.3. So this is the rest of the 4 kilobytes chunk. The reason why it's size 4088 because the header occupies the 8 bytes. Note now, let's imagine that a chunk of memory is requested, say of size 100 bytes. To service this request, the library will first find a chunk that is large enough to accommodate the request. Because there's only one free chunk, size 4088, this chunk will be chosen. So this is what the library does. Since after the let's imagine you have this operating system here, and then you have this unallocated space, and you have this space that start with 16 kilobyte, and that you have heap. Once you request the space, you don't need to allocate the size or to specify the size. The malloc library will automatically know the size. So it will find the free list among this space. So as we can see, we have a free list of 4088. So it will allocate that in this space, in this heap position in the physical memory. This chunk will be chosen, then the chunk will be split into two, because that's the splitting and coalescing, just like we discussed in the previous video. One chunk big enough to service the request and header as described above, and the remaining free chunk. Therefore, after that, you will update the free chunk, or the library will update the free chunk. Assuming a 8-byte heap, an integer size, and an integer magic number. So 8-byte header, that includes the magic number as well. So the type of the size is an integer size, and then the type of the magic is also an integer. The space in the heap now looks like what you see in figure 17.4. So you can see the size now is 380, so it updates the header as well, not just the free list. So this is what the malloc library does after you allocated space on that heap. Thus, upon the request for 100 bytes, the library allocated 108 bytes out of the existing one free chunk. Also, instead of just allocating that, because the library are programmed to allocate as well a header with the header size that data structure we created, it will allocate two size, a header and the actual allocation. So, thus, upon the request for 100 bytes, the library allocated 108 bytes, including the header, out of the existing one free chunk. And then it returns a pointer. So that's the program of the library. It returns a pointer to the mark PTR in the figure above. So here, it returns that pointer, stashes the header information immediately before the allocated space for later use upon free. So it stashes that header information, so it's saved that somewhere for later use in case the program marked that as free, and that's how it frees the space without remembering or requiring the program to remember its size. So it manages it in the background and shrinks the one free node in the list to 3980 bytes. Also, another logic for that is it also shrink that to 3980 bytes, since 4088 minus 108 is equals to 3980. Now, let's look at the heap when there are three allocated regions as each of 100 bytes or 10 gig, including the each of 100 bytes or 108 including the header. A visualization of this heap is shown in figure 17.5. Oh my god, where's the 7.5? So here's the 17.5. As you can see therein, the first 324 bytes of the heap are now allocated. So there's 3 allocated regions, each 100 bytes or 108 including the header. So as you can see, there's 324, 100 times 3. So as you can see therein, the first 324 bytes of this heap space are now allocated. So 100 bytes still allocated, 100 bytes still allocated, and then oh my god, I think that previous yeah, I think it should be 17.6. And thus we see 3 headers in the space as well as 100 bytes region being used by the calling program. The free list remains uninteresting, just a single node point by the head, but now only 3764 bytes in size after 3 splits. But what happens when the calling program returns some memory via free? Where's that 17.5? I just wonder where. Just a moment, guys. Yeah, I think yeah. So this is how it looks like. You have a 100 bytes total to 324 bytes including the header of the heap are now allocated, and thus we see 3 headers in that space as well as a 100 byte region being used by the calling program. So these 3 100 byte region are actually being used by the calling program because it calls 3 100. So the free list remains uninteresting, just a single node pointed to by head. So these are the free list. So this is actually the free list we are talking about in our algorithm earlier. This here until pointing downwards, or the downwards are pointed by the head. So that's actually how it knows the free or available space. This is how we create that free list, or how the malloc library create the free list or track the free space. But now only 3764 bytes in size after 3 splits. But what happened when the calling program returns some memory via free? So in this example, the application returns the middle chunk of allocated memory. So it here is about to be allocated by calling free 16,500. So why is it 16,500? You say because 16 kilobytes is 384, 16,384 bytes plus 108, meaning we're trying to free this type or 100, this part of the heap. So the value 16500 is arrived upon by the start of the memory regions, which is 6384 plus 108 of the previous chunk, and the 8 bytes of the header for this chunk. So 6384 plus 108 plus 8. Let's calculate that. Yeah, so that's 16500. So what it does is that the reason why it only deleting that is because it only deletes that the space. It's not the header. As you can see, we started at here at this SPTR. We didn't include its header. when we are deleting or freeing it. So this value is shown in the previous diagram by the pointer. Now let's copy the 17.6. So here's the example. Now you have this new head. You have a free chunk of memory here. You have a free chunk of memory. So what do you do? The library immediately figure out the size of the free region and then adds the free chunk back onto the free list. Assuming we insert at the head of the free list, the space now looks like in 17.6. So the library immediately or automatically figure out the size of the free region. So the size of the free region are determined using this header. So it knows that it has a size of 100, and then it adds the free chunk, which is 100, back into the free list, which is this 3764. So as you can see, the arrow, assuming we insert the at the head of the free list, the space now looks like in 17.6. So what's the issue there? There's a lot. So now we have a list that starts with a small free chunk, 100 bytes, pointed to by the head of the list. So the header are still there. It was pointed by the head of this list, and a large free chunk 3764. So this 3764, that's our previous unallocated space after we have allocated 100 bytes. Our list finally has more than one element on it, and yes, the free space is fragmented. So now we have a list that is fragmented because we have a list here, list element, and then we have list element in the middle. An unfortunate but common occurrence. So one last example. So that's where the coalescing came, because we want to avoid this, scattered elements of free space in our memory to manage the space efficiently. One example, let's assume now that the last two in use chunks are freed. Without coalescing, you end up with fragmentation. So let's also assume that the last two in this list, which is the 100 allocated, were free as well. Now without coalescing or without adding it up, you end up with fragmentation like this: now free, now free, now free. So you have this 100, 638, 467, 16492. It's scrambled. So this is the main issue with variable allocation of size, which we don't encounter in fixed variable or fixed size in page table, which we're gonna discuss in the next video. So here, figure 17.7. As you can see from the figure, we now have a big mess. Why? Simple. We forgot to coalesce the list. Although all the memory is free, it chopped up into pieces, the appearing as a fragmented memory despite not being one. So again, we arrive at the problem of non-contiguous memory, because again, we assume that in this when trying to serve a variable size allocation from malloc, we try to assume that the request is contiguous so as to make it simple, but we were gonna make it more complicated in multi-processing request. So that's more complicated, but here we were just gonna deal with the basics first. So we forgot to coalesce the list. Although all the memory is free, it is chopped up into pieces, thus appearing as a fragmented memory, despite not being one. The solution is simple. Go through the list and merge neighboring chunks. So that's the key. You need to merge, go through the list, search all the elements in the list. So since we tracked that using the data structure earlier, the first paste, we were gonna use that to track it, right? So we use that to track the elements in the list, and after we track that, we will search every element, and then we will gonna merge the neighboring chunk. So since it's contiguous, it's an array where it's easy to determine what index who. Um, so when finished, the heap will be wool again. So again, the heap is an array as well. After you combine those or merge those adjacent index, the free chunk will be wool again, just like when we start, which is the I think 4 kilobytes. So growing the heap, we should discuss one last mechanisms found within many allocation libraries. Specifically, what should you do if the heap runs out of space? The simplest approach is just to fail. So these are all mechanisms, but one last mechanism that we will discuss is what if it ran out of space, like the requested space is not available anymore from that heap space allocated by physical memory. One of the simplest approach is just to fail or return null. In some cases, this is the only option, and thus returning null is an honorable approach. Most traditional allocators start with a small size heap and then request more memory from the OS when they run out. So most traditional allocators are like that malloc library. They start with a small size heap and then request more memory from the OS when they run out. So in the physical memory, you have OS and then a small heap. So most of these allocators or traditional allocators like malloc, they start with a small heap and then just request to the OS as they go. And we will also discuss that type of malloc, because this malloc is also a library, which means that they are also algorithm. So they could like choose to save those most frequent and then just request to the OS more memory when they needed. Typically, this means they make some kind of system call like SBRK in most Unix systems. So just like a malloc, so the separated list or stub, which we will gonna discuss later, use this SBRK to tap into the OS to request for more memory for the heap, to grow the heap, and then allocate the new chunks from there. To service the SBRK request, the OS finds free physical pages, maps them into the address space. So in the low level view, the OS actually find a free physical pages, and then it maps them to the address space of the requesting process. So let's say the process requests to grow a heap because there's not enough heap memory anymore because it's being used by other processes. The OS, after it was called using SBRK, it will map it to the virtual address of the requesting the virtual address of the requesting process, then returning the value of the end of the new heap. So it will return the value of the end, which is the bound, for the process to be able to know the size of the new allocated space. At that point, a larger heap is available and the request can be successfully serviced. Now, basic strategies. Now that we have some machinery under our belt, let's go over some basic strategies for managing free space. The ideal allocator is both fast and minimizes fragmentation. So the ideal allocator, just like any algorithm, uh, maximize the time and space efficiency. Unfortunately, because the stream of allocation and free request can be arbitrary, after all, they are determined by the programmer. Any particular strategy can do quite badly given the wrong set of inputs. Thus, we will not describe a best approach, but rather talk about some basics and discuss their pros and cons. Best fit. So, the best fit strategy is quite simple. First, search through the free list and find chunks of free memory that are big or bigger than the requested size. So this strategy, it search all the free elements using the data structure we have initiated earlier, um, and then it only find a greater than or equal memory size, then return the one that is the smallest in the group of candidates of the group of the free space that is greater than and equal of the space it is looking. This is the so-called best fit chunk. It could be called smallest fit too. One pass through the free list is enough to find the correct block to return. So only one traversal of all the elements are enough to find the correct block to return to the process or the programmer. However, there is a cost. Naive implementation pay a heavy performance penalty when performing an exhaustive search for the correct free block. When performing an exhaustive search. So there is a cost in this. If you didn't implement it well, there's a lot of search costs. So remember the search in previous video about algorithm cost a lot when in terms of time and space as well. Worst fit. The worst fit find the largest chunk and return the requested amount. It keep the remaining large chunk on the free list. Worst, most studies show that it performs badly, leading to excess fragmentation while still having high overhead. So if you have a workload that you know that from time to time you're gonna get this large block that is important from the process, like large request of space, worst fit may be better. But be careful if it's not, because most of the time average happens. So if you most likely request like just enough, it may not be the appropriate one, because this strategy leads to fragmentation, which is what we are trying to avoid in this space efficiency. So the first fit method simply finds the first block that is big enough and returns the requested amount to the user. So first fit, once it finds the first fit, it doesn't need to traverse through the list. So it saved the search time efficiency. As before, the remaining free space is kept free for subsequent request. So after it find that, it doesn't need to search. Therefore, the other spaces are now free. So there's a time for other process to request. So if you have a workload that needs to satisfy that immediately, those small bump of requests, then first fit may be better. First fit has the advantage of speed, no exhaustive search of all the free space are necessary, but sometimes pollutes the beginning of the free list with small objects. So the beginning or the start of the free list, or the first index, it most of the time pollutes that. So if your workload will be harmed by having a small block at first, because that again that also determine your search time efficiency. If the small first few blocks of the array does not meet the load, it could affect your time as well. But in theory, this is better than best fit and first fit, because you're just finding the first fit necessary, but sometimes pollutes the beginning of the free list with small objects. Thus, how the allocator manages the free list order becomes an issue. So the allocator, the library, since it manages the free list, it could have a code that use an address-based ordering that manage those small objects at the beginning by keeping the list ordered by the address of the free space. So it can use like a sorting, like making things order by size, for example, keeping at the larger size at the start of the array. It could alleviate that weakness. Coalescing becomes easier and the fragmentation tends to be reduced. So coalescing in that case is easier and the fragmentation tends to be reduced, but there's also an implementation cost on that. So do you have a developer that could implement that address ordering inside of this already complicated malloc allocator library? Next fit, instead of always beginning the first fit search at the beginning of the list, the next fit algorithm keeps an extra pointer to the location within the list where one was looking last. So it keeps an extra pointer. So it implements a pointer on its code, on its library, within the list, like the initiated list data structure we created earlier, where one was looking last. So the idea is to spread the searches for free space throughout the list more uniformly. So its idea is it will spread the searches for free space more uniformly because you started at the last instead of always starting at the start of the array, thus avoiding splintering of the beginning of the list. It doesn't need to be an array, but in this case mostly it's an array. But any data structure you will have to start at the beginning, right? So the performance of such an approach is quite similar to first fit, as an exhaustive search is once again avoided. So let's ignore headers and other details and provide examples on how this algorithm operates. So here head, let's example 10, 30, and 20, and then you have end null. So this the basic diagram. You have head, the allocated spaces for the heap 10, 30, 20, and you have null. If it's not those are outside of the allocated, it means that it's out of bounds. So it doesn't meet the bound of this allocated memory, therefore the OS will return null. Now assume an allocation request of size 15. So a best fit approach would search the entire list and find that 20 was the best fit, as it is the smallest free space that can accommodate the request. So the resulting free list is head 10, 35 null. As happens in this example and often happens with the best fit approach, a small free chunk is now left over. So that's its weakness. There's a small free chunk left over. A worst fit approach is similar but instead finds the largest chunk. In this example 30. The resulting list is head 10, 15, 20 null. The first fit strategy in this example does the same thing as worst fit, also finding the first free block that can satisfy the request. So it does the same the worst fit that find it the free block that satisfy the request in this list. Again, it starts with the head, right? 10, 15, 20. The difference is in the search cost. Both best fit and worst fit look through the entire list. First fit only examines free chunks until it finds one that fits. Both best fit and worst fit look through the entire list. First fit only examines free chunks until it finds one that fits, thus reducing the cost. Again, both best fit and worst fit look through the entire list. First fit only examines free chunks until it finds one that fits, thus reducing the search cost. So again, in worst fit, it find the biggest one on the list and then try to keep a large allocated block. Not try it tries to satisfy a large request from the program. This example just scratched the surface of allocation policies. More detailed analysis with real workloads and more complex allocator behaviors like coalescing are required for deeper understanding. Other approaches. Beyond the basic approaches described above, there have been a host of suggested techniques and algorithms to improve memory allocation in some way. So beside this basic approach, these are the recommended approach to or techniques to improve memory location in some way. So these are the algorithms that has been developed by mathematicians and programmers to be able to make the space efficient or the fragmentation. Segregated list. This is what I'm saying earlier. So if a particular application has one or a few popular size requests that it makes, keep a separate list just to manage objects of that size. So it will keep a separate list to manage that size of the most frequent request. So other than the free list, it has a separate list or segregated list for those most frequent requests. All other requests are forwarded to a more general memory allocator. The benefits of such an approach are obvious. By having a chunk of memory dedicated for one particular size of request, fragmentation is much less of a concern. Moreover, allocation and free requests can be served quite quickly when they are of the right size, as no complicated search of a list is required. Again, the benefits of such an approach are obvious. By having a chunk of memory dedicated for one particular size of request, fragmentation is much less of a concern because allocation and free requests can be served quite quickly when they are of the right size, as no complicated search of a list is required. So you minimize the search and also you are able to serve those most common requests quickly, and you're able to serve the right size of the needed by the processes instead of having this fragmentation where you split a space and return some space and then have the block unallocated because it's not contiguous. So just like any good idea, this approach introduces new complications into a system as well. For example, how much memory should one dedicate to the pool of memory that serves a specialized request of a given size? So what algorithm would you use to know the size of that segregated list for that common pool of requests, as opposed to the general pool? So one particular allocator, the slab allocator by Hoover engineer Jeff, which was designed for use in the Solars kernel, handles this issue in a rather nice way. Specifically, when the kernel boots up, it allocates a number of object caches for kernel objects that are likely to be requested frequently. So it allocates an objects. They created an operating system or kernel that when boot up, allocate a number of object caches. So a memory caches for kernel objects that are likely to be requested frequently, or it does this on the software kernel itself. For those commonly requested process in the system, such as locks, file system, enums, etc., it caches those requests. So it allocate an object just for those processes in the system. So the object caches thus are segregated free list of a given size and serve memory allocation and free request quickly. So again, the object caches thus are each segregated free list. So these object caches are equivalent to the segregated free list we were talking earlier. But in this case, you have a segregated or object cache for locks, object cache for file system, segregated list for lock, segregated list for file system of a given size and serve memory allocation and free request quickly. Therefore, they serve the more memory allocation and free request quickly because there's certain allocated for them. It can be more efficiently allocated and with the right size without any space fragmentation. When a given cache is running low on free space, so this is the code that makes that efficient, it requests some slabs of memory from a more general memory allocator. So only when it runs out of free space, it requests to more from a more general memory allocator so that they maximize the space or they don't throw away wasted space. The total amount requested being a multiple of the page size and the object in question. So the total amount of the requested is a multiple of page size and object in question. So let's say you have one process that requests like this size 5. So there and the other processes are being used in that object of the object cache of the kernel or the segregated list. Let's say that process is 5 and it will that object kernel will ask the general memory to provide it a multiple of that 5. So let's say 5 times 5 like 25. So that it has another 25 space, but it doesn't requested always. You don't have this free space always. You only request that when needed, but it is in multiple. So being a multiple of page size and object in question. Conversely, when the reference counts of the objects within a given slab all go to 0, so the reference of that object all goes to 0, the general allocator can reclaim them from the specialized allocator. So the general allocator can reclaim the memory. So those are the designed to reclaim or the general allocator or the OS are designed to reclaim that memory from that allocated segregated list if no ones are using it to make the space more efficient, which is often done when the BM system needs more memory. So it is done as well when the on the other hand, the OS, the general OS virtual memory needs a space. So they're just trying to maximize when needed, when they request the space when needed. So the slab allocator, and also notice here, we use the word reclaim because it's the OS that's doing all the work, not the particular segregated free list. So the slab allocator also goes beyond most segregated list approaches by keeping free objects on the list in a pre-initialized state. Again, the slab allocator also goes beyond most segregated list approaches by keeping free objects on the list in a pre-initialized state. So it start or this object or it's pre-initialized so that it can be easily activated. So Bonwick shows that initialization and destruction of data structure is costly. So in its code, since this locks a file system request have these various states that it goes through, this object saved that state, that initial state on it, so that when the request doesn't need to initialize, it will just hack it immediately. So by keeping freed objects in a particular list in their initialized state, the slab allocator does avoid frequent initialization and destruction cycles per object, and thus lower overheads noticeably of that object again, or the modes in its state, like what we discussed in the previous video about page. So body allocation, because coalescing is critical for an allocator, some approaches have been designed around making coalescing simple. One good example is found in the binary body allocator. In such a system, free memory is first conceptually thought as one big space of size 2 raised to n. So because coalescing is earlier we discussed a segregated list, which designed to fix the fragmentation by the split. Now there is an allocator that designed to optimize the coalescing, which is the addition of the space. So one good example is found in the binary body allocator. In such a system, free memory is first conceptually thought of as one big space of size 2 raised to n. When a request for memory is made, the search for free space recursively divides free space by 2 until a block that is big enough to accommodate the request is found, and a further split into 2 would result in a space that is too small. At this point, the requested block is returned to the user. So again, in such a system, free memory is first conceptually thought of as one big size of 2 raised to n. When a request for free memory is made, the search for free space recursively divides free space by 2 until a block that is big enough to accommodate the request is found. So let's say we have a heap of 64 kilobytes. This algorithm will recursively divide that until it is equal or greater than the block that is being requested. So, and a further split into 2 would result in a space that is too small. At this point, the requested block is returned to the user. Here's an example of 64 kilobyte free space getting divided in the search for a 7 kilobyte block. So notice the algorithm that is best for this. I think it's binary search tree, because you can easily, or the search efficiency is faster. In the example, the leftmost 8 kilobyte block is allocated as indicated by the darker shade of gray and returned to the user. Note that this scheme can suffer from internal fragmentation, as you are only allowed to give out power of 2 size blocks. So since we're optimizing for coalescing, we're not optimizing for splitting or for the segregated list, which is managing the fragmentation. So like in any system, we need to choose a trade-off, what we want, what is more important with regards to our workload, as you are only allowed to give out power of 2 size blocks. So the beauty of body algorithm is found in what happens when that block is freed. So when that the operation for free, it removes that complexity, because it coalesces. The system are designed to coalesce or to combine or to merge the free space automatically and in O log n time efficiency. So when returning the 8 kilobytes block to the free list, the allocator checks whether the body 8 kilobyte is free. If so, it coalesces the 2 blocks in a 16 kilobytes block. So how it does that in the back end. So the core check if the block is free. So if the space is equals to free, the allocator then checks if the body of the 16 kilobyte block is free. If so, it coalesces these 2 blocks. This recursive coalescing process continues up the tree, either restoring the entire free space or stopping when body is found to be in use. So it will stop when body is block is in use. So other ideas, one major problem with many, you can research this further, this algorithm, there's many out there, but these are algorithm that is found to be efficient on handling the space and time efficiency of the problem of virtual memory for external fragmentation. So other ideas, one major problems with many of the approaches described above is their lack of scaling. Specifically, searching lists can be quite slow. Thus, advanced allocators use more complex data structure to address this cost. So with these basics allocators, which was implemented in the past, the issue is with its time, which is the searching for this for the memory for the allocation for the requested program. That's why a complicated or sophisticated allocators are implemented with more complex data structure to address this cost, trading simplicity for performance. So most of the allocators we have on our operating system now have a sophisticated code that trades it for the complexity for performance. Example include balanced binary trees, place trees, or partially ordered trees. Given that modern systems often have multiple processes and run multi-threaded workloads, something you'll learn about in great detail in the next section, it is not surprising that a lot of effort has been spent making allocators work well on multi-processor based systems. So a more complex algorithm are actually being used today, of course, in the to trade performance in especially multi-processor system. Here we just discuss, the basics. We relax assumptions. We just discussed non-multi-processor, if there's that word, but it's not. We discussed the how it used to allocate, how the operating system used to allocate in the past for us to better understand the basics so that we can understand those complex. But there is another data structure which is the page. I think it's not data structure, it's a way to store the memory. It's a fixed size so that it removes this need for creating those complex algorithm, which we will discuss in the next video. So this is actually how the modern operating system use or structure their allocator library. So in this chapter, we discuss the most rudimentary forms of memory allocators. Such allocators exist everywhere, linked to link into every C program you write, as well as in the underlying OS, which is managing memory for its own data structure. So our modern OS use this, inherently, like allocation in the heap, etc. It's just different algorithm and structure. And the C program or the C programming language use this as an allocator. So as with many systems, there are many trade-offs to be made in building such system, and the more you know about the exact workload presented to an allocator, the more you could do to tune is to work better for that workload. So the more you know what workload are you gonna implement on that operating system, the better you know in implementing that workload, making a fast, space efficient, scalable allocator that works well for a broad range of workloads remains an ongoing challenge in modern computer system. Again, making a fast, spaced, efficient, scalable allocators. So that's the third parameter, which is scalability, which make this complicated algorithms for modern operating system. Aside from space and time complexity for a broad range of workloads remains ongoing challenge in modern operating system.